Okay, example 1. Determine the Thevenin equivalent circuit between the nodes A and B. So there's the circuit. Nice little picture of it there. Get it copied down for yourself. All right, turn that off. Okay, so I have it copied down here. Determining the Thevenin equivalent, and I might even add on here and Norton as well, because as we know, through source transformation, once you have the Thevenin, you can get the Norton for free. So there's lots of different ways that you can approach this problem, this specific circuit. And so I'm going to try to show you several different ones. I am by no means showing you all of the different ways that you can do it. We're just going to have a look at some of the ways. The first way we're going to do it is using the steps that we outlined for finding the Thevenin equivalent. I want to start out with the steps because that's kind of how you're going to have to do it when they get a little bit more complicated, and it's the way that's always going to work. So you're definitely going to want to know that way, though it doesn't really help you build a good intuition of what's going on. So the first way that we'll show is using the steps. We'll say using the steps. So remember, the steps was finding first. I just find it easier in my head. It makes sense. It doesn't really matter which order you do. If you find RTH first or you find the Thevenin voltage first, it doesn't really matter. I just like finding this one first. So the first thing you want to do is turn off all independent sources. Turn off all independent sources. So that means if we had dependent sources, like that, you don't turn that off, okay? You can't turn those off because they are dependent on something else. And if you turn it off, then you're saying that that thing, which it is dependent upon, is zero. When you turn these two guys off here, we have two of them. When you turn those off, you're saying the voltage source is now 0 volts, and you're saying the current source is now 0 amps. The only way, and we showed this just sort of briefly, the only way you can make the voltage source have 0 volts is to have it become a wire. Then you have the 4 ohm resistor, the 12 ohm resistor, and the only way that you can make sure that there is 0 amps going between this two is to have nothing. So you just leave it there. Then you have a 1, node A, and node B. You don't need to draw all of these circles. I just kind of like to do that here while I am demonstrating these. So that way you can kind of see what's happened here. And again, I want to highlight what's happened here is for the voltage source, in order to turn it off, we have to make it have 0 volts. Connecting a wire causes this node and this node to have precisely the same voltage, which means the voltage difference between them is 0, therefore 0 volts. Doesn't mean the voltage is 0, it just means the voltage difference there is 0, and that's turning that off. Right, because otherwise with the source there, the difference between these two nodes is 32. The current source we need from this node to this node originally has 2 amps going from the bottom node to the top. Now it has 0 because there's no direct connection there at all whatsoever. So that's how you do that. Okay. Now what we do is we look at, is there a way that we can just easily calculate the overall resistance between here. So we want to imagine that we're taking some sort of measurement device. We've done this before, across there, across nodes A and B, and figuring that out. Well, we see the 4 and the 12 are in parallel. So that's going to be, get our calculator out, 4 plus 12 inverse 3. So that's going to be a 3. And we've done this exact kind of thing before. It's just finding total resistance. We did that. So notice these two are in parallel. which is in series with this 1, right? You go from the A through the 1, through both the 4 and the 12 in parallel, back over to here. So then you end up with this. And we see then pretty easily that that overall resistance will be 4. So the Thevenin resistance is therefore 4. Now for the Thevenin voltage. For the Thevenin voltage, we rewrite the circuit. You don't have to rewrite it, but I'm going to. You just need another copy of it, but we're going to do stuff to it. So I want to have a copy of it down here. So just bear with me while I rewrite it. There we go. Okay, so that's the circuit again. And what we need then is the Thevenin voltage. So that's going to be just what is the voltage between there and there. We're going to need to know like which one's the lowest one and the highest one, but for now we can just think about like what's the voltage difference between those two. So this is where there's a whole slew of ways that you can do it. There's pretty much just one way, one good way to get the Thevenin resistance, although technically there's another way and we'll show that in just a moment. But to get just the Thevenin resistance, this is how you want to do it. For the voltage, there's a whole bunch of different ways that you can approach this. And the first way we're going to show is kind of the least intuitive way, maybe. The way that doesn't help you really build an understanding of how the circuits are built. And anyway, whatever. It's to just do regular old mesh analysis. So the first way we'll do it is mesh analysis. So we'll do a mesh analysis first. For that, we'll set up I1 over here and I2 over here. And by now we can see I2 must be equal to -2. So we got that one for free. Notice we don't need to worry about this. Why don't we need to worry about this? Because there's no current that can flow out of there. Remember, A and B aren't connected to anything, right? They're just sitting there. So there's no current that can flow from this node through this resistor at all, right? So that means the voltage at A is the same as the voltage here. There's nothing happening, there's no mesh there. We could just kind of ignore it. In fact, you could replace it with a wire if you wanted to as well. For I1, the I1 equation will be 0 equals, I'll just start down here. We hit -32 plus 12 plus 4 is the two resistors in there, I1, minus 12I2. Simplifying this a bit here, move it up, plus 16I1 minus 12 times I2 was -2. There we go. Minus 32 plus 16I1 plus 24. What is that? So that's going to be 24 minus 32 is -8. Minus 8 plus 16I1. So that I1 is equal to 8 over 16, or 0.5. Right on, so I1 equals 0.5. Okay, cool. So how does that help us? Well, A and B are there. And since we already said the voltage here and here are the same, then that means that we could find the voltage across this current source, which is tough. But that's in parallel with this 12. So if we could find the voltage across the 12, we could find the voltage across A and B. So let's do that, because it's just in parallel, because there's no current going through that 1 ohm resistor. So we want the current, and we've kind of seen this when we were doing mesh analysis before. So this will be our 12. And we'll just go ahead and set up, there's some current going this direction. We see then I1 is going in that same direction, so it adds to that. I1. I2 is going in the opposite direction, right? It's going to loop around and go up this way, which we have I12 going, the current there going down, right? We defined it going down. I2 is going up there, so it's going to be minus I2. Plugging in the numbers, 0.5 minus -2 plus is going to be 2.5 for that current. Therefore, the voltage across this guy here will be a high voltage here and a low voltage there because of the direction we drew this current flowing from high to low. The voltage there is going to be I, which is 2.5 times 12. 2.5 times 12 is 30. 30. And that's going to be our Thevenin not resistance, Thevenin voltage. Okay. So then we always want to go ahead and draw a equivalent circuit here. There's our A, there's our B, and here's 4 and 30. Right on. Remember, we can also get the Norton one then too. We got the Norton for free. Squeeze the Norton in here. A, B, resistor stays the same. Current source goes up because this is minus on the bottom, plus on the top, making sure they're going in the same direction. That current source will be I equals V over R by Ohm's law. So that would just be 30 over 4. And that'll be whatever that is. 30 over 4 is 7.5. Right on. 7.5. 7.5. So there you go. Good stuff. Now let's go ahead and check it. Let me pause. All right, so this is us checking it. So we can do, oops, common. There we go. Resistor, wire, get a current source going here. A wire there and there, resistor there, a wire there, and adjust these values. That was 32. This was a 4, 12, 1, and 2. Get the current to go a little slower. There we go, right on. Alrighty, so that's that one. And then we said that a 30 in series with a 4 would be the same thing. So let's change this to a 30. Change this one to a 4. Okay, and now remember, when you are checking these two circuits, this one and this one, we're saying are the same. However, you can't really check it that well completely unless you actually complete the circuit somehow. I recommend just throwing a resistor in. You could use a wire, but I just kind of like the sureness of using a resistor. You should be able to check the voltage. The best way to check the voltage is going to be to just look at the voltage difference between the bottom and top wires. Sometimes when you do two circuits here, you're going to need to throw in a ground. So just go ahead and make one of them be ground. That makes it 0 volts. So if I move my head, that makes the one that you connect the ground to 0. That the one on the top says 30. That says 30. What you can also do then is throw a resistor. Throw a resistor in. There we go. And let's make it something where the current will go. There we go. We'll make it a 7. And you just check the current. It's 2.727. 2.727. Right on. So those are the same. Let's check our Norton equivalent while we're here. So I'm just going to copy paste this one. and we said it should be 7.5, and this should be in parallel, and it should be a 4 there. Whew, that's going pretty quick, isn't it? Oh, it sure is. Throw a ground on there. Look at that, 30 volts, right on. Let's put the resistor on there. What? 2.727 amps. Okay, now what putting the resistor on there does is it proves that they are equivalent circuits, that this, what's drawn here, is equivalent to what's drawn here between the two nodes. That it has, and when we say equivalent, we mean it has the same effect on anything that is, on anything that is put between the bottom and top nodes. That's what we mean, and that's why putting the resistor on there and making sure that the current and voltage across it are the same is what helps you do that. So now let's take a look at some of the other ways that you can solve this same problem. Okay, so we've checked our work, and now what we want to do is see about some other ways to solve this. So one of the other ways that we can do it is using some combination of analysis, measure node, and source transformation. So let's look at one of those ways now. I'll redraw the circuit. Maybe I could have these redrawn already beforehand. I don't know. I'm sort of, doesn't take all that long. I think maybe when they get more complicated, I'll do that, you know, maybe. 1, there's A and B. Connect that up. Okay, so there's our original circuit. Now, one of the things that jumps out to me is that the 32 and the 4 are in series, and we saw with source transformation, that means we can make it a parallel resistor and current source. This current source and resistor are in parallel, so we could make that into a series voltage source and resistor. Let's do this one, these two parallel guys there first, and see what we end up with. So we'll draw the 32 and the 4, since those aren't changing. Give ourselves a bit more room since we're making something in series. Now all we're going to do is we're going to write the resistor, and it has to be in series with a voltage source. That's where we're going to put the voltage source. That takes up these two things right there, became these two things. So that means we skip this wire, and now we're on to writing the 1 ohm resistor and node A. And this one skips over to B. So you kind of see how that works? I know I haven't filled in anything here yet, but you see how that works? We have these two just kind of became this one wire. If you prefer, we could always do it a bit more slowly. And we could write it like this. And we could say, all right, that becomes, we could go like this and say this, these nodes here combine together. Like this. You could do that. And then maybe you can kind of see it as kind of a, ooh, I'll do it this way. Kind of like a this, they're parallel, and then they become series in one line. All right, that's kind of what's happening there. Now, just like going from voltage source to current source, I'm going to go the other way. You just look at what direction the current source is pointing, plus minus. It's pretty easy. Resistor stays the same. Okay, now we want this voltage here, right? We want, what is the voltage difference there? What is that? All right, that's what we want. Just like before, there's no current that flows between this resistor, so the voltage at A is the same as the voltage there. So if we could find the voltage difference between B, this one guy here, and that node, we would be rock solid. But it's tough to do. So what's the voltage there? I drew the plus and minus in, but I didn't write out the voltage source. So the voltage value there would be just the I times R, which is 2 times 12, which will be 24. So to find this voltage difference, we could start at B and say that's 0, and then go up, and you see we're going to have to add, since we're going from minus to plus, we're going to have to add 24. So at this point, it's 24. And then we go up here, and we gain or lose however much voltage difference there is across the 12. But we don't know that, don't even know the current between there. What we do know is that the current only goes in this loop and none goes in there. So what we can do is this combination of mesh and voltage analysis. We can make life a little bit easier here by, again, seeing that since there's no current flowing here, this circuit is really the same in sort of analysis terms. It's not actually the same because of this 1 ohm resistor there. But in terms of the analysis we want to do, it's the same as plus minus 24, It's the same as this, right? If this is just a wire coming off of that, it does nothing, right? It does absolutely nothing. So then we can just combine these together. So we can combine the voltage sources together, since they're minus and minus. We can combine those together to be 32 minus 24, which is 8. And the resistors combine together to make 16. And now we can find out this current. All right, so we'll say there's that. And now we can find out this current, and we see that I will be 8 over 16, which is 0.5. Oh, sound familiar, right? 0.5. We had that here with that mesh. I1 was 0.5. Doesn't I1 look awfully familiar, yeah? 0.5 again, pops up. So we take that information now that this current here was 0.5, and we bring it back over to here to mean this had to have been 0.5, right? We just look back, say this was 0.5. So then now we know the current going through the 12. Now we know the voltage across the 12. So we have this 12 ohm resistor, and it has some current of 0.5 going through it, which means the voltage across it, plus minus, the voltage across it will be 6, 12 times a half. So when we go from B to A, I'll put in here 6 volts, just to remind us. When we go from B to A, we start at B and we say this is 0. Once we cross this voltage source, we now have plus 24. When we cross the 12, since the current is going down, we gain voltage, and we gain 6 volts. So that means that this will be 30 volts, which will be our Thevenin voltage. That's another way to do it. The way that I would end up doing this problem, though, and this will be, I think, the last way. Yeah, it's the last one that I had planned. So this is the last way that I'll show. Like I said, there's a whole bunch of different ways to do this, but this one will be using only source transformation. I don't know why, but I usually like to use source transformation as much as possible to simplify the circuit as much as can be done through source transformation before I actually sit down and write out any equations. I just think it makes it a little bit easier. So what we'll do is we will quickly and perhaps somewhat sloppily, rewrite the circuit again, because now you've seen me rewrite this darn thing like 5 or 6 times. I don't even want to speculate how many times you've seen me rewrite this darn thing. There. Okay. So, like we saw, these guys here were in parallel, so we could make them a series thing. So you could do that. It's fine. You would just kind of end up in the same situation as we did before. But we could also make these two into parallel. So let's have a look at that. So we're going to change those into parallel resistor and current source. And so that's going to be kind of like that. You're just splitting it open that way, right? And then, of course, you don't normally write them like that with the little bow looking thing. You would normally want to square it up, make it look professional. So that's all we're doing here with this guy. So we're going to do source, resistor. All right, so that takes care of those two. Now we're at this node and this node, right? We're at those two. So that's going to be the 12. And then we have the 2. And then we have the 1, A, B. The nice thing about doing source transformation continuously is that sometimes you can get the whole problem solved all at once. And that's what we'll see in this case. Remember, the resistor stays the same, and it's going to be up because it's minus plus. Oh, and the current value, the source for that, will be 32 divided by 4b, 8. These two current sources, they're facing the same direction, so they add up. And they're parallel. So that's a 10 now. These two resistors are in parallel, so we can add those together. I think we already did that. Pretty sure we already did that. That's a 3. Then you have the 1, B. All right. Now, oh, well, what's going on here? Geez, well, let's just do it again. Source transformation the other way around. Turn the current source into a voltage source. When you do that, we'll do voltage source. I'm really bad at writing resistors from bottom to top like that. So resistor stays the same. Let's go over here for B. And 1. And that'll be 8. All right. So I did that one a little bit quickly. So remember, these two combine together, right? It's kind of just working this backwards. We're going to see this picture right now. We imagine them as bringing these two nodes and these two, I guess technically they're not nodes, these 2 points and these 2 points together to make this little bow shape. And then you smack them together and it makes a series connection. All right, that's all that's happening there. And now these two are in series. Oops, sorry, getting ahead of myself. The voltage here will be I times R. So that'll be 30. 30. So this will be plus minus 30 for A, B. And there you got the whole thing, right? So you don't really need to go through this step process every time. Sometimes you can get away with doing just a whole bunch of source transformation and you get it all for free. So I kind of like doing it that way when at all possible. I very, very, very highly recommend that you push yourself to do the source transformation method whenever you see a circuit where it could be used. even if it doesn't end up making it any simpler. It's good practice. Instead of having to do the step process, because as you see, the step process kind of involves doing a whole bunch of extra stuff that you don't necessarily have to do. All right. A lot of times students like the step process because it seems easier. You're being told, do this step, then the next step, so on, so on, so on. It's very straightforward, very objective. But this way of doing it will really help you build a better intuition about how to analyze these circuits and get you to a point where you can do it very, very quickly. Okay? Maybe you have to have a calculator on hand, whatever. But it'll get you to a point, promise, of being able to do it much faster if you can look at this circuit and say, hey, I could combine these. Still would be in a tight spot. I could swap these, I could transform these into this. That's going to give me an 8. I can add it to the 2 to get a 10. I can combine those. Okay, that's going to be a 3. And then I could transform that again. The 3 and the 1 will give me 4. So I automatically know Thevenin resistance is going to be 4. And then the voltage is going to be the 10 times the 3. You can do this very, very quickly just in your head without having to write down all of these intermediate circuits once you get to a point where you've practiced it a lot. So I want you to just push yourself to do that. So what I would recommend doing is you look at this, your original problem, and you think, okay, I'm going to transform this. Think in your head, what is that going to look like? What is that going to look like? And then write it down. Write down what you thought. And then see if it's right. If you have to go through this to see if it's right, then do that. Then once you're here, think, okay, now what can I do? Okay, think about what that's going to look like. And then go for it, okay? And push yourself as you move forward to think further ahead. Think 2 steps ahead. Think 3 steps ahead. And write that down. And then check through doing the intermediate steps. That will really help you build up speed while doing this so that you don't get bogged down writing out a whole bunch of math equations, a whole bunch of intermediate steps where mistakes can arise. And of course, mistakes can arise when you're doing these things in your head as well, but the more you practice doing it, the more it'll just kind of start to make sense a little bit. Just like how you can tell me what 2 plus 2 is without having to count them out on your fingers, but there was a point in your life where you had to count them out on your fingers, okay? So it's the same sort of idea. So hopefully that helps. We got more examples coming, so look out for those. Got to get my mouse working here so that I can stop the recording. Come on. I'm sure there's a keyboard shortcut to stop it, but I don't know what it is.